Hello and welcome to another stats warm-up. All right, so we're going to continue our look here with hypothesis tests, only this time instead of dealing with proportions, we're going to be dealing with means. All right, so the EPA has determined that safe drinking water should contain no more than 1.2 milligrams per liter of copper. You are testing water from a new source and take 30 water samples. The mean copper content in your sample is 1.36 and the standard deviation is 0.18. There do not appear to be any outliers in your data. Do these samples provide convincing evidence at the 0.05 significance level that the water from this source contains unsafe levels of copper? All right. Now, because we're specifically testing for unsafe levels of copper, that informs that we're going to be doing a greater than or a one-tailed test because we're testing, are we above sort of the 1.2 there? All right, so we'll start with our nulls, our null, and that's that the mean is equal to 1.2. Then we'll get our alternative down, which is that the mean is in fact greater than 1.2. All right, the problem tells us we're going to use an alpha of 0.05. Now, we should check our conditions at this point. So we are taking like samples. It doesn't specifically say random samples, but I think we can kind of assume that there. Our sample size is above 30. So we're going to be okay even if it's not totally normal, especially considering it tells us that there don't appear to be any outliers in our data. All right, so that's gives us a pretty high level of confidence that we're going to be okay with everything that we're doing here. So to actually perform the test, all right, we're going to go to stat tests. We never use z-test, all right, because we don't have the population standard deviation, and there's no reason we ever would. So we're going to stick with t-test here. All right, we don't have data, but we do have statistics that the problem gives us. Our null is that the mean is 1.2. Our sample average was 1.36. Our sample standard deviation was 0.18. We took a sample size of 30, and we're testing to see whether it is greater than 1.2. All right. So when we do that, all right, we get a test statistic of 4.87, we'll say. All right, from that test statistic, we end up with a p-value. And then be careful, notice that this is e to the negative fifth, so that's really 0.00001827. And then x bar is just giving us back our x bar, s of x is just giving us back our s of x, and then n is our sample size. Now, I should have written this all down to show my work. So I should have shown that I was using a u of 1.2. I was using the x bar of 1.36. I was using an s of x of 0.18. I was using an n of 30. And I was doing a test to see if we were greater than the mean there. All right, so again, that's kind of me showing my work so that if something goes wrong and one of these numbers isn't right, I can sort of trace it back and figure out what happened. All right, so I calculated my test statistic. I found my p-value. I can now write my conclusion. All right, so what this is showing is that there's a really, 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 really tiny chance of getting this sample result when your sample size is 30 if this is true. All right, and since the odds of getting these results are so tiny, our conclusion is that this is probably not true. All right, so because our p-value is under 5%, which is what we established as our alpha, we reject the null and accept the alternative. So in this case, if we kind of look at, what this is saying in the real world is the new source has too much copper. All right. There's convincing evidence that it's above that threshold of 1.2, so we probably don't want to use it. All right, number 2, sweet corn of a certain variety is known to produce individual ears of corn with a mean weight of 8 ounces. A farmer is testing a new fertilizer designed to produce larger ears of corn as measured by their weight. He finds that 28 randomly selected ears of corn grown with fertilizer have a mean weight of 8.25 and a standard deviation of 0.8. There are no outliers on the data. Do the samples provide convincing evidence that the fertilizer had a positive impact on the weight of corn? So again, this is telling us that we're doing another one-tailed test, and we're seeing if it's increased. All right, so you always have to kind of read the question and sort of pull that out of what sort of test you're doing. All right, so our null hypothesis is that the mean has stayed 8 ounces. Our alternative hypothesis is that the mean has been increased to above 8 ounces. We're going to stick with an alpha of 0.05. Now, we should kind of go through the conditions here. 28 is, pretty likely less than 10% of the population. We selected them randomly. N is less than 30 here, but it does tell us that we have no outliers, and weights tend to be pretty consistently normally distributed. So we're close enough here that there's no real concern that we're going to run into any problems here. So again, we're good to go. So we're going to do our t-test because we never do z-test. All right. So tests, t-test. All right. My null is going to be that the mean is 8. My sample result was that it ended up being 8.25 with a standard deviation of 0.8. So 8.25, sample standard deviation of 0.8. Our sample size was 28. And we are again testing to see whether it is greater than our null hypothesis. So if we calculate this out, all right, we get a test statistic of 1.65, which yields a p-value of 0.05. Let's just say 49. Right, 0.0549. All right, so this one's close. All right, it's very close to our threshold, but the rule is it has to be under the threshold. So even though this is super close, we're going to say, sorry, there was almost a 5.5% chance of this happening, which is still low. There's only a 5.5% chance of getting a sample result this large or larger when you're taking a sample of size 28, assuming this is true. But 5.5% is just a little too high for us. So because our p-value is over 5%, which again is our alpha, we fail to reject the null. All right. So we might be suspicious. We might think that maybe it helps, but we don't have enough evidence to really be confident that the fertilizer is doing anything. All right. Maybe it's worth more study. All right. Maybe it's worth a larger sample to get a better idea. But based on what we've done so far, we don't have a lot of confidence that we're necessarily actually above this mean of 8. All right. It was unlikely to get 8.25, 5.5%, but we set our threshold at 5%, so we fail to reject the null in this situation. All right, let's take a look at the back. All right, does too much sleep impair intellectual performance? Research examined this commonly held belief by comparing the performance of subjects on the mornings following 2 normal nights of sleep to 2 nights of extended sleep. The order of these 2 treatments was determined randomly. In the morning, they were given a number of tests of their ability to think quickly and clearly. One test was for vigilance, where the lower the score, the more vigilant the subject. All right, so lower scores are good. Think of it kind of like golf if need be. So does too much sleep impair intellectual performance? Does it basically increase your vigilance score? All right, so again, because a lower score is better, impairing intellectual performance would mean your vigilance score increased. All right, so got to be careful with these. Sometimes just the way things are measured and then what you're actually looking at, it can sometimes be counterintuitive. But in this case, lower score is good. So increasing the score increasing would be a sign that too much sleep impaired intellectual performance. So when we have these before and afters, we don't perform the test on the before, we don't perform the test on the after, we perform the test on the difference. So we're going to start by calculating extended minus normal. All right. So for this first one, 8 minus 8 would be 0. 9 minus 9 would be 0. 17 minus 4 would be 3. 2 minus 4 would be negative 2. 21 minus 12 would be 9. 16 minus 11, 5. 6, 12, 7, and negative 8. So that's the data that we're actually going to be checking. All right, we're seeing whether this gives us evidence that too much sleep hurts intellectual performance. All right, so again, our null hypothesis is always the statement of no difference. So when you're doing these before and after, no difference would imply that the mean is 0. When you subtract these two values, they're averaging out to 0 because there's no difference. All right. We're testing, did we impair intellectual performance? So again, because a high score is worse, we're testing if U is greater than 0. Now, if you'd done the subtraction in the other direction, then you could have tested whether U was less than 0. The greater than or less than can kind of flip based on the order that you're doing the subtraction in. But I did extended minus normal, and because a higher score is bad, I'm testing is U greater than 0, and I'm doing it with an alpha of 0.05. Now, in this case, I only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations, which is not a lot. So it's not the worst idea to kind of make sure that those follow a normal distribution, because otherwise I might not actually be able to perform this test. Now, it doesn't really appear that there's any major outliers. I go as high as 12 on the positive side. I go to negative 8 on the lower side. And then I have a bunch of things scattered in between. So I think we're okay there. But what I'm going to do, or what I've already done, is I've put the data into L1. And what I'm going to do is I'm going to run a normal probability plot on that. And if you remember, what we're hoping to see is that it works out to be fairly linear. And if it's linear, that gives me a good idea that this data is normal. And that I can proceed with my test. And you can see here that my normal probability plot is very linear. So let me just kind of sketch this right here. I've got, this is my normal probability plot. And this is very linear, which is for us a good thing. All right, it means our data is normal. So we can kind of proceed with this, even though our sample size criteria is not really met. All right. So now that we've kind of put that to bed, let's go to our stat tests. We're still going to be using t-test. Now, I just put the data in there, so I could just use the data feature because all of my data is in L1. Remember, when we're doing these, we don't use any of this stuff. We only use the differences. So I can just say, all right, my data is inputted into L1. I'm testing against a mean of 0, and I want to test to see whether we are greater than that one. So I can just say that I'm using the data and that my list is L1. Frequency is 1, that's fine, and I can calculate it. And then from this, I get all my sample statistics anyways. So it tells me that X bar was 3.2. It tells me that S of X was 5.865. And it tells me that N was 10. So, all the same data either way. But more importantly, there's my test statistic of 1.73. And there's my p-value of 0.0593, we'll say. All right. So based on this result, this is basically saying, hey, you looked at the average difference between extended and normal sleep. You got an average of 3.2, but it had a standard deviation of 5.865. So given that your sample size was 10, if we assume that there's no difference, there was almost a 6% chance of getting a result similar to this, all right? This or higher, all right? 6%, not huge, but it is above our threshold. So we have to say we fail to reject the null because our p-value is over 5%. And again, that 5% represents the alpha value. All right. So main thing with these is just to realize that when you get this before and after data, you're not doing the test on the before, you're not doing the test on the after, you're not combining them into like one big long list. You're taking the difference between those, the difference between normal and extended, over and over and over again. You're getting all of those differences. This is the data that you care about. This is what you care. Is it normally distributed? Can I run the test? This is the data that you're using the test on. So it really, the problem is going to give you like the before and after, but it's only there to get the difference. All right. Everything from that point on involves using the numbers in the difference. And then your null for these is always going to be that there's no difference. All right. The null hypothesis we've said from day one is the statement of no difference. So no difference means that when you subtract them, you're expecting to get 0. All right. And then your alternative can be greater than, less than, not equal to, what have you. And from that point on, it runs like a normal test. All right. There's nothing different. It's just really how you get your starting values that you're going to use when you're running one of these. Okay. So last question. A consumer advocacy group tests the mean vitamin C content of 50 different brands of bottled juices using in each case a t-test of significance in which the null hypothesis is the mean amount of vitamin C that is on the nutrition facts label for the brand of juice. They find that 2 of the 50 juice brands have statistically significant lower vitamin C's than claimed at the 5% level. In the context of this study, what does statistically significant mean? All right. So it implies that in those samples, the calculated statistic was far enough from the assumed mean Far enough from the, I skipped a word there, from the assumed mean that it was unlikely caused by sampling variation. All right, so our sample result was so extreme that it's unlikely to have occurred just because of sampling variation. It's more likely that our initial assumption was wrong. So it implies that those samples that in those samples the calculated stick was far enough from the assumed mean that it was unlikely to be caused by sampling variation. It was unlikely caused. I don't think I love how that sounds. From the assumed mean that it was unlikely a result of sampling variation. Let's go with that. I like that better. Unlikely a result of sampling variation. Now, is this an important discovery? All right. Probably not. All right. The researchers conducted 50 separate tests. With an alpha of 0.05. Okay. That means they have a 5% chance of making a type 1 error. Right? Since they did it 50 times, 50 times 0.05 equals 2.5. All right. This is their expected number of mistakes. So yes, they found 2 that ended up statistically significant, but it's possible that those were just type 1 errors. And if you do something 50 times, you are going to expect to get a couple of type 1 errors. In this case, you're expecting to get about 2.5 type 1 errors. So the fact that you got 2 well, we don't know that they're type 1 errors, but the fact that you found 2 that are statistically significant might not actually be meaningful. All right, that's where replication is important. And you'd probably have researchers go back and retest those brands and see whether the result is consistent, or whether it was probably just, a fluke from the one weird sample that you collected. All right, so hope this was helpful. Again, same general process for a hypothesis test. It's just now we're looking at t-tests that involve means. So you're using a slightly different menu on your calculator, but you're still providing the information. You're still interpreting in the same way. And then the only extra wrinkle is these before and afters where you focus on the difference, not the original data. All right. So hope this was useful. If you have any questions, let me know, and we will go from there. All right.